later again. So what I will say today will be a review of Q-learning and SARSA, just a tabular form, and not the neural network. So just the tabular form of Q-learning and SARSA. But I will start, I think some of the students joined later. So I will start from an introduction to artificial intelligence, to reinforcement learning, and then to the other topics. So for the exam, you will need more knowledge than what I will say today. So today is just these two topics based on the on your major. If you are computer science, or if you are studying artificial intelligence or applied artificial intelligence, you will have two lectures different. So in each of the subjects majors, the two lectures are different, but this is in common. That's why I have invited all of you to listen to this, and then for revision of the two other like specialized topics, we will have other sessions. So let's start from artificial intelligence. Can you hear me also when my back is to the board? Yes?
Yes.
Thank you very much. Okay. So artificial intelligence has many different branches. One of them is machine learning. Machine learning talks about the statistics of data device for prediction and also for decision making, predicting the best action or predicting what will come in the future. Machine learning itself has different branches. It can be supervised learning. It can be unsupervised learning, and it can be reinforcement. Pardon me? Yes, artificial intelligence, of course, this question will not be in the exam, but artificial intelligence is an attempt to write programs which can adapt themselves to solve problems. So you had other types of problems that they were rule-based, which means that you say, if then else, or if based on if then else, if this happens, do that. You had a fixed, let's say, understandable problem. But artificial intelligence is different in the fact that usually it's used for big problems, in problems that the complexity is so high that a programmer cannot consciously sit and decide what will be the conditions, what will happen, either the amount of data which should be analyzed is big, or we say the problem is too non-linear, problem is not easily solvable, so we use artificial intelligence. The way that our subconscious solves problems, we want the problems to be solved that way. And it is usually understood as a black box that has an input and output, and we don't know what is inside. So what is inside is the result. I mean, what is inside has an initial random state, and then it gets optimized to achieve a goal. So we have an input. The output is a function of input, and this function should be learned. So we want to find out what is this function. We want to find out what is this function. For example, you have a function, let's say you have collected some data like this, X and Y. X is your input and Y is your output. There is a function, for example, f of X, which gives you the Y. So let's say f of X can be simply Y multiplied to 1. So our black box is this function. We want to find what is inside. Then in the process of optimization, we look for the best parameter to describe this function. So this is basically, let's say, function approximation. And neural network can be understood as this, which has roots in functional analysis. So it means you have a functional, which is function of functions, set of functions which are inside another function, and you want to find out the parameters of that function. But let's go back to our artificial intelligence, say in general, machine learning, and sub-branches of machine learning. Supervised learning. Supervised learning is methods are the set of methods in which you find the parameters of this black box based on already known output. So you know what is the output, you know what is the input, and you optimize your model to give you the proper output. For example, you can say that let's say like that curve. This is input, this is output. This is X, this is Y. So the input is 1, the output is 2. When the input is 10, the output is 20, the input was 8, the output was 16. So if you want to have a system which could produce output given input, it means that X goes in, Y comes out. 10 goes in, 20 comes out. If you want to make such a problem, the system may produce some random output at the beginning because it's not optimized. Then what happens is that you guide the system, you supervise the system to give you the desired output. That is supervised learning. You have supervision, you have guidance. The machine learning systems, I said, there are systems which are adaptive. It means at the beginning, they are not what we want. They have a random state. Like a child which doesn't know any language. Now, she's born in China. She should learn Chinese. If she was born in, I don't know, England, she would have to learn English. But at the beginning, the child doesn't know anything. So the child adapts to the system. So first speaks wrong. All children have mistakes. They say something, and we correct them, or they correct themselves by kindness. That is supervised. Means you know what should be the outcome. You adapt the parameters of the system to give you what you want. This is supervised. Unsupervised learning are for discovering the world. It means you want to classify some objects, and classification itself is a supervised method, but your world is very complex. You don't know how to describe things to later, based off those descriptions, you could categorize them. Let's say you have microscopic images of cells. You want to say which of them is cancer, which of them is not cancer. perhaps you want to see what are the characteristics. What are the characteristics? How can I basically describe one of those cells based on color, based on what? These characteristics may be very complex. It's not just one word based on what. In order to extract the building blocks of the data, we use unsupervised methods. And they may have other goals. For example, dimensionality reduction. You have a data, for example, let's say from sales shop, you have let's say a big Excel file with 2,000 columns. Then you want to reduce this space so that a classifier could classify it. You want to reduce the space. Let's say I want to be able to describe each product not with 200 characteristics, but with 20. So perhaps one of these characteristics is a function of 10 of them. So instead of saying that it is straight and it is, I don't know, it is solid and it is like this, like this, like this. You say TV is one word. Yeah. This one word can describe kind of object, but this encapsulation of characteristics is called dimensionality reduction. Now you have a table, instead of 200 columns, it has 20 columns, and you can classify it better. So dimensionality reduction is there. Sorry, the unsupervised methods are there to study and transform the space. But there are other problems. There are other problems in which we don't want to really predict something. Prediction is a part of it, but we want to take actions. We want to take actions to achieve a goal. And the system, the world is so complex that you cannot simply write a program for it. For example, I gave this example that when I'm walking, if you study millimeter by millimeter, actually I will be never in the same state that I am now. I'm changing myself. My weight is changing because I'm spending energy, and everything is changing. So the system is adapting. Perhaps someone will hit me and I may be falling. So you cannot simply write a program, say, lift your leg and put it forward and it is walking. No, this is not what you cannot say what to do. You can't say what you want. I want you to move two legs. That's it. We cannot give more details because the space is very complex. For these systems, we need to adapt. So the system, the agent, it's called agent, needs to adapt to achieve a goal. In our example, the goal is, let's say, walking. So I had given this example in the class. I'll repeat it. Now let me first draw a diagram. Perhaps that is better. Okay. I said we have an agent, which is in a world, say in an environment. This agent has to achieve some goals. In order to achieve those goals, the agent will take some action. To take some action. The action, this is the agent. The action will affect our environment. And the environment will react in the form of a reward or a punishment. Let's say, so this was the action, which was the but it's not just the reward. When I move toward my goal, let's say the goal is moving forward or achieving something, each step I take, my position in relation to the environment changes. The environment should also give me a state. Yeah. The environment should also give me the state. If you have them capital letters. And these three are building blocks of reinforcement. State, action, reward. You are in a state, you take an action, you get a reward, the state changes. The state is changing. Okay, then I had also this example of the cart pole. If you remember, you have a stick, you want to keep it direct. You want to keep it direct. By moving left and right, you want to stay, you keep it. If the stick was longer, I could show it better. So if it is falling to the right, my hand should go to the right. If it's falling to the left, my hand should come to the left. So my goal was to keep this stick straight. So here, what are the parameters of this state? Let me share the screen and show you. Perhaps better if I share the screen instead of trying to draw it. So this is the stick that I was talking about. Do you see my screen?
Yes.
Okay.
Yes, but
So this was the stick that I was talking about. And so the action is going to the left or to the right. So these are the actions. Go to the right, go to the left. How do I describe the state? The state of this stick is either is falling, is standing. So the state can be described with angular velocity. So it means with which speed it's falling down. With the velocity itself, this is the velocity. And with its position, let's say from the base. Yeah, so we have x, which is the distance from the base, the speed of movement, velocity of the movement, the angle, and angular velocity. So what do we see here? In order to describe the state, we need 5 or 4 parameters. 1, 2, 3, 4, actually 4 parameters. One state needs 4 parameters. Actions are 2, and this can be variable. So let me again, let's go back to the board. So if I want to, let's say with numbers, explain if an action in a state is good or bad, what should I do? I have a table. This is our table. Each row of the table is representing a state. We are getting state 1 or state 2 or state 3. Pay attention. In the card plot that we saw right now, each of the tuples that we had, x, velocity, angle, angular velocity, each of these is one state. So these S1, S2, S4, inside them, we have 4 numbers. But now we don't concentrate on that. We have states, and here we have actions. Action 1, action 2. So these are our actions. What do you think I should write here to complete the information about the problem? So we want to see if you are in state 1, is it better to go to the right or to the left? Is action A better or action 1 better or action 2? Action 1, for example, is going to the right. Action B is going to the left. Which of them is better? I would say, let's say, if I say 5 is very good. I write a 5 here because I've tried it. And a 3 here, a 4 here, a 2 here, a 5 here, and a 0 here. So what would this mean? It means that if you are in action in state 1, if you take action 1, this is 5 units good. If you take action 2, it is 3 units good. So if you want to take the best action, you will take action 1. If you're in state 2, if you take action 1, it is 4 units good. Like when you write this quick questionnaires, so you are evaluating a human, and you say that, let's say, if your teacher is good in teaching, give it a score between 1 and 5. If you are satisfied, you put 5. This is like that. But we are evaluating actions. We are giving values to actions. What are these? To go back, where could we find these numbers? These are rewards. So these are our rewards. If you remember,
Doctor,
yes.
quick question. Now, do you remember the AI model where it had to choose different what do you call it? Different paths to reach the goal?
Yes.
Now, in that model specifically, what would be considered a state? The position or what exactly? The
Yes.
position of the so that would be a state.
Yes, so you had this grid. For example, this is one state, this is another state. So if your agent is here, the state is 2, 2. So if you want to show the state in numbers, it is state 2, 2. But you may say that I call it state 5. 1, 2, 3, 4, 5. So let's say this is state 6. You can say this is state 6. I call it, and someone asks you what is in details. You say it is position 2 and 2. And here, let's say this is state 10, which means position 3 and, let's say put it here, it is position 3 and 4.
Okay, so in a program like Cartpool, what would be considered a state?
So you quantify your states. You need 2 tables sometimes, in one of which your states are written. I mean, the details of the states are written, and each of them has a label. Let's say you have a dictionary in which the key is the name of the state. The value is the coordinates. Or it can be that you say, I have a list of states. So this can be shown even with like a table of states in which the index is state number. You can populate this, you can make this table bigger. Let's say the two first columns are the states. So I say 2 and 2, and this is the rest are the actions. But we don't want to make it so complicated. You want to separate tables. Like you remember in databases, you had two tables, one with the foreign keys connected to each other. So this is state number. And these are the details of your states. And 3 and 4 and so on. It's a 5 and 1. So here you have the index. Naturally, it at least has indices. And then you have another table in which let's say the number of the index, the number of an index represents the state here. So state 1 is in row 1. You come to the row 1 and see what are the specifications of the state 1. Next time your object is in the row 5, column 1, then you look, this is state 3, you come here, then you see which action is better. So somewhere you translate your states, but when it comes to Q table, the rows show the number, the code of the state, and the columns are representing the actions. Is it clear?
Yeah, so they're both connected, yeah? The
Yes.
state and the action in a specific table. So for example, like with Cartpole, it would perform specific actions depending on what state it's in.
It can take any action, but we may choose the best action. Yeah. So in Cartpole there are just two. In Cartpole there are just two actions.
Yeah, left and right.
Sometimes this action left is better. Sometimes action right is better. You are right after some time. Logically, yes, we are finding a correlation. That which of them is better, and we always take that. So you are right. You said that's yeah, that is also correct. Then what did we want to say? State actions. So this is. Do you remember what was the name of this? The name of this table. We call it Q table, correct? We call it Q table. This is Q table. Q table. We have a table here. If you want to write a program which extracts the information from this Q table, you may write a function. Yes. Yeah, I would write a function, call it Q, that would give me the reward, because in Q table, I write reward. What would be the input to that function? The state and the action, yes? State and the action. If these are two numbers, then the function looks into this table and finds the best, sorry, and finds the reward for us. For example, if I write 2 and 2, this function Q will go here, row 2, column 2 will give me a 2. So we will have a function like this that takes a state and action and gives me the reward. But we say that it is about learning and optimization. It's about learning and optimization. And the ones who are watching it is through the computer, are these visible?
Yes.
Okay, thank you. So when we talk about optimization, it means that the system is learning. It means that at the beginning it's not good and it gets better. How do we get better? By repeating. Yes, we practice, we repeat, we do the same thing many, many times to get better. If you want to learn a language, you cannot say one word one time in life and then you say that you have learned it. You do it over and over. While, I don't know, while playing football, you should do the same movements many, many times. So, or you should actually try to achieve the same goal many, many times. First, you are bad, then you get better and better, then you are excellent. What does that mean? I'm doing the same things many, many, many times. What is changing? What is updated? Because the states are the states of the specifications of my work. If I play football, the earth doesn't change. What is changing? I am changing. What is changing? Yes, but what is changing? What is changing? The action, no, state is the word. The state cannot change. State is the word. So I am walking in this room. The room doesn't change. The action also is I'm just moving. What can I do? Yes, I do. The reward is changing. The reward changes. Still, it means in each situation, the value of all possible actions that I can take changes in each possible. In the card poll, the state, the set of states is, even if it is unlimited, by card poll moving in the world it doesn't change. The states, the world can change, but we don't have it under control. What we have under control is the value of our actions. I want to see in each situation, what is the best thing I could do? It is falling. Should I go left or right? I evaluate them. I would look at this table. Going left is better, so I'll go left. But at the beginning, perhaps these numbers were different. Actually, they were different. At the beginning, perhaps all of them were zero. So by time passing, they get better and better and better so that I can achieve my goal. Perhaps the best thing would be having a 5 here, a 0 here, a 5 here, a 0 here, so that it is very clear to where we should go. Like very binary. So the thing which is changing is the reward. The thing which is changing is the rewards. Yeah, the reward is changing. What does that mean? What does that mean? That the reward is changing. What is changing? These are changing. Yeah. So the job of this function is not just giving us values, it is also setting values for us. It is not just giving us values. So if I say QS is, let's say Q23 is 5, then the program comes, we don't have 3 states here, let's say 1. Yeah, the program comes to the row 2, column 1, sets this to 5. Yes, and then if I ask it, say, for example, R1 is Q11, it goes to column 1, row 1, column 1, takes 5 and puts 5 to R. So with this function, let's say we can control what is in our Q table. Yeah? With this function, we can control what is in our Q table. But we say that learning means updating this. Yeah? Learning means updating this. What does it mean? It means that the Q, S, and A has been something, and something else is overwritten. Yeah, something else. We are writing something else to what exists. We are changing it. Can we just simply change it without looking what it has been here? Because the action that we take has been based on this. So something was in my mind, then I took an action, and now based on what I see new, I should update that. It means this was falling, it was written here that action left is better. I went to the left, then I don't change it. It was good. I may add something to it. Or I may not change it. But I'm not going to reduce it. So the value is X is what we have here. So it means that what we have on the right here, should be something S and A. So something should come left and right, up and down of this, yeah? This something should come, so this should be modified and rewritten here because we want to modify this based on what we had. So what do you think should be there? I had this example that if you go to a new country and you want to adapt to people who are there, we do not get one person and copy him or copy her. Then that person may be himself or herself an outlier. No one likes that person. So you want to be accepted by the whole society. What do? You look at this person, you may change a little bit toward him, and then you look at the other person, you change a little bit toward him, and then you may see that the specifications of the first person you have seen is not seen anywhere else. You reduce the specification. So this, let's say here, most of people have white clothes. The first person you have seen had been completely in black clothes. Then after sometimes that black should vanish from your memory. Slowly, the change should be slowly. So let's say I have had a value here, a default value here. Then I want to change this, which is a reward. I want to change this reward. It should be based on the new reward that I see, yes? Based on the new reward that I see. So the reward that I had recorded in the past either should go up or should go down, yes? Either you add something to it or reduce something from it. Yeah? But what is that something? It should be the new reward that we see. So I take an action, I see a new reward. So people, I had like a black dress. I say no one likes me because here is not accepted. Then shall I consider this as the last answer and accept? No, how do I know? But it is based on that. So this is immediate reward. This is a recorded reward. What you see in the queue, it is what has been written here in the past. This is recorded reward. It is in the queue table. But what you see here is the immediate reward, that you are seeing. So if I want to change this based on this, and I don't want to overwrite this and that. So I could simply say, I remove this and say new old reward removed. I write the new reward on it and finish. But this is not what we want to do. What we want to do is looking how much the reward has changed in comparison to what it has been before. How much the reward has changed. So the change always in all machine learning problems, the change is with a subtraction. So the new reward, immediate reward, you subtract from it what you had in the past. You remove this. So immediate reward, false reward. So now these two are the same. Actually, these two are the same. But here we are talking about the difference. If the new reward is bigger than the previous reward, this will be a positive value. Yes? So if R, which is immediate reward, if this is bigger than Q, S, and A, then this change will be positive. But how should I call this? What do you think? So you have let's say this hypothesis, a value for this reward, and now you have something new. I would call it error. So the error will be bigger than 0. Then it means that we are adding something to the previous reward. So you had a recorded reward here for the action. So you had state action for this state. If in this state you take this action, the reward will be this, and you have recorded it. Yeah? But now you're adding or to it or removing from it. What should be added? So, or removed. The difference between the immediate reward, that means the reward that you have now, and what you had recorded before. So, if the immediate reward is bigger than the recorded reward, you will have a positive value, and something will be added, so it will increase. And in the case reward is smaller than immediate reward is smaller than the recorded reward, then your error will be smaller than 0, then this will be subtracted from it. But we said that we don't want to do big changes. We don't want to make big changes. You had a recorded reward, you saw something new, but you are not going to make a big change. If you want to slowly change, what you would do, you would divide this by something. Let's say that something is called alpha, and alpha is a value smaller than 1 and bigger than 0. Let's say alpha is 0.1. Which means that in each step, when you see that what you have recorded in the past and what you see now are different, you take this difference and just 10% of it will be added to the previously recorded reward. So, yes.
I just have a quick question because I don't get it. If the reward is bigger than the QSA, will it update the table or not?
Yes. So I said through this, you can update the table or read from it. Yes.
Yes.
Through this. So this had a value. This had a value, let's say 4.
Okay.
Let me give you an example. Let's take this one. What is Q2 and 2? The Q2 and 2 is 2, yes?
Yes.
Then I go to the state, let's say this is state 2. I take action 2, and someone says that, hey, what you did was actually very correct. The score of that action, so what you did, for example, I saw someone and I say, hi, I'm a child. Say, very good. In the past, someone had told me, why did you talk to a stranger? But now someone saying, hey, you're a polite child. It's not true, actually. You did a good job. It is actually 5. Then, shall I change this immediately to 5? No, because let's say my father told me this is correct. My mother said it's wrong. I don't know how the other people say. So I should be careful not immediately change, because both of these people are good. There is something that I don't see. Yeah? In some conditions, saying hi is good. In some conditions, it's bad. So what should I do? Shall I change this immediately to 5? No. I say, okay, I will listen to my father, but just a little bit. So in the past, I had a 2 here. It was a 2. This is a 2. Then I take this 2 and add just 10% of the difference. Just 10% of the difference. Let's say the difference. Now my father said it is correct. In the past, I had value 2. The difference is 3. So what will be overwritten on 2 is 2 plus 10% of 3. So then what will happen? I come here, I write 2.3. Yeah. So I changed it a little bit. I took the difference between what I had in my mind, perhaps because of the training of my mother, and then what my father told me, but I'm not going to overwrite, because perhaps I don't know these people. Then I take just a portion of the difference and add it to what I had in my previous training. In the states that you see someone older than you, you say hi, or you don't say hi. In the past, I was punished, now I was rewarded. So I changed it a little bit. Perhaps now I'm older, I can say hi. Yeah. So perhaps I have changed, perhaps the word has changed. So you change it a little bit. You change it a little. So this is, the formula is not yet complete. Let's say taking an action, not let's say always, taking an action puts you in a new state. Yes, I want to reach that TV there. I want to reach that TV there. And if I take the action toward this, I'm in a state in which going toward the table or TV is in a way achievable. But if I go to this direction, it's another way. So I may go to a state that makes the life more difficult, or go to a state that makes the life easy. That should also be considered. It can be that there is an obstacle in front of me, or there's let's say, there is something dangerous here. But that I will reach in 2 steps from now. If I come here, from now on, it will be more difficult than if I go to the left and then go toward my goal. So I should also consider that. Not only immediate reward, but also the future reward. How do I add the future reward to this? So the future reward, when I'm in the future state, there also I can do different things. Yes, there are different actions I can take. Now I can go to the left, right, left, straight, right, or go back. I can do all these 3. When I move forward, I can do all these 4. I can do all these 4 again. If I go to the left, again, there's a same situation. So if someone wants to tell me that if you take action A, you will be in a situation that the life is difficult, because the best action that you can take even that will not help. Or once you can tell me, if you go to the left, the best action that you can take can actually help you. You go to the left, and then you go to the right, and then you achieve your goal. So how can I write this mathematically? Up to now, we are having the current state, current reward, recorded reward, immediate reward. Now we want to go for the future. What is future reward? Future reward. So I'm in a state in the future. Let's call it state, the future state. Future state is called S prime. And when I'm there, already the action, let's call it A from future action in the state S prime. So, and then how can I write the future reward? How do I write the reward? Reward comes from the Q table. So in Q table, you have a state in which you got an action and you got the reward, and you have a function Q that can give you those values, even can set those values. So the future reward can be written like this: Q S prime A prime. This is my future reward. So shall I simply write the future reward there? So let's say I open this and write Q S prime A prime, because we want to change slowly. This is the learning rate. This is called learning rate. And want to have a slow change. So I add also the future reward to this. I can add, but again, it will be too big, because what comes in the future is less certain. We should give less value, or we should trust the future less than what we see now. We will come back if we have time till the end of semester. It has another way of explanation when it comes to the math. You always have, we call it discounted sum of future rewards. Means the farther you go to the future, you consider the reward less. So I cannot simply add this. I can add, but it means that I trust the future and now at the same in the same value, in same amount. But I don't want that. So what I do is I reduce this prime. I reduce it by a value, by a portion, let's say coefficient. I call it, this is gamma. Let's see, let's this also be 0.1 or 0.9, anything. This should be gamma also. Gamma and alpha should be both less than 1, bigger than 0. It means that I take just a portion of the future reward in consideration. Which future reward? Which future reward? Any future reward? Because when I'm in the future, I can take different actions. Which future? That has different, I mean, we can look into the future in different ways. But if we always take the maximum future What? On the action A, it means A prime. So you change action to you think about future. So when I am in the next state, I can take 4 actions based on what is written in Q table. I check which of them is better. I consider just that one. This is called, we can call it also argmax. It means that the argument that makes the reward maximum. Max. If you consider for the future reward, you consider the best, the highest reward that you can take. This is called learning. This is called Q-learning. So this is the formula for Q-learning. You have this document shared. Yes. This is being recorded, so you can go to the beginning. So you came a little bit later. So this is recorded. I will share the video. So this is called Q-learning. It means that you are in different states. I'm standing here. I should decide which action is the best. I have a goal. This is the family of artificial intelligence problems that you adapt to achieve a goal. You are not pre-programmed. You don't know. Like you have seen these movies of the robots. You hit the robot, but it doesn't fall. So this robot is no programmer can write all conditions of in which direction or angle the robot will hit. No programmer can do that. You train it to take actions, go back, go to the right, or they have the stepper motors, which degree, which of them should move to stay stable. So which action or set of actions should be taken in each state. And the value of those actions are written something in the Q table, and the Q table is updated. If it is updated this way, we call it Q learning. Okay. Let's write the names of these parameters. Alpha is learning rate, with the speed that you update your current recorded reward. R is the immediate reward. And this max A prime, S prime, A prime is the maximum future reward. And then you have gamma, which call it the discount factor. And the discount factor tells us how much we trust the future, how much we take the future into the account. If the discount factor is small, it means that, or it is 0, it means you don't consider the future. You can, the world is so dynamic and changing and unstable, you cannot trust it. And you cannot take it into the account. Now I want to give you an example.
Doctor,
Yes.
really quick, because I didn't understand how the future max reward would be calculated in the first place? Like, how would it know, like, what the future max reward is, and how would it act based upon that?
Read it from the Q table. Because we
Also
said
from the
that,
Q table.
yes, because we said that we have an optimization, we have learning. I have gone this way 1,000 times till I learn to behave correctly. So, and each time I have gone through this table, I have updated the values. There are places that I have not seen, I have not watched. Yeah, there are such places that I have not seen. And those values there, the rewards are 0. But by time passing, new values will come. And at the end, you will have hopefully a full Q table. And now we want to go deeper, how actually we are going to fill our Q table. Unfortunately, in this room, I cannot use the projector because the projector is actually in a right place. But the ones who are using Teams, perhaps the students who are here, one of you logs into the Teams. Shall can you please, one of you please log into the Teams so that when I share my screen and I show the code, you can see what I'm showing. Yeah, in the computer perhaps it's easier. Yeah.
Doctor, just a quick question. What was
Yes.
the discount factor for?
So the discount factor, so we say that we take this future reward, what will come in the future. Like what someone tells me, after you take this action, you go to the next state, and that next state, if you go to the left, you get that amount of reward. Just how much am I going to consider that reward for updating the current? So it can be that there are 2 states in front of me. One of them looks good because if I go through this movement, let's say there is someone in front of that door. If I go out, it will pay me more than if I go through that door. But later there will be dangerous. Yes, if I am there, what should I do? If I am there, what should I do? And I'm going to consider when I am there, which action which bring the biggest reward. Yeah, but how much am I going to trust what will come there, or how much am I going to consider that future reward to update the current one? Let's say we have for this is, let's say, S2. So we are in S1. If we take action 1, we will go to S prime, which is S2, and then S2 action A prime is, let's say we have here S3 action 1, yeah, S3 action 1, which gives me a reward which is written there. But how much of that do I want to add to my current reward? Let's say I want just 20% of it. That 20% is the gamma. We call it the discount factor, because what you see here, yeah, it is a discounted future reward. Discounted future reward. Theoretically, we should have added, we should have had this sum of discounted rewards. The farther I go to the future, the less I consider the reward. How? I increase the discount factor, but in this formula, we don't have that. We don't have. This tells me how much I'm going to consider the future reward for updating my current rewards. So in this state and under this action, we will have recorded a reward. Now what we want to do, we want to update it. We want to update it based on the difference between the immediate reward, what I had recorded in the past, but without some portion of the future reward. Immediate reward, previous reward, future reward. But this is true. Previous reward means in the same state. This is in the next state. So we don't want to consider the next state too much. So now what I will do is showing you an example. Showing you an example. Do you see the Visual Studio IDE?
Yes.
Yes. Okay. So, do you also see it? You should. Do you see the shared screen? No. Yes. Do you see the cartwheel moving?
Yes, Professor.
You can see.
Yeah, we can see it.
So that's enough. Yeah, so you can see it, yeah, from this one. Okay. So. Actually, I can. Sorry for the technical problem. So I will. You don't see me on the camera. I will run the code again, and I will run the code again. Let's see. So this is the cartwheel just in the test phase. It means that I have trained it. I've trained it. The training is finished, and now what is happening is just using the results of the training. Just using the results of the training. But first, I will tell you something about the performance. You see, if you run the code, you will see some numbers here being shown. So what do these numbers mean? So we have the reward. The reward being shown here. The reward is 500. Here the reward is 303. What does that mean? So first of all, for the ones who joined the course later, this cartwheel and other environment with which you will work, these come from the Gymnasium or Gymnasium library, which gives you not only this visual let's say, appearance, this visualization, but also functionality to implement reinforcement learning. So let's see what were these numbers here. I said that I talked about going one time toward the goal and then repeat it, and repeat it, and repeat it. What you see here is not the training, it is the test. It means that while the card pull is moving, it's not learning. But what is the reward? The number of states, the number of steps that the card pull is standing straight is added up. And it says that, for example, in this case, 264 steps, the card pull could be straight. In this case, 500. In this case, 500. Why are they different? Because the initial state is random, and if you start from some of them, you will get 500. In some other state, you may get 451. So these are what you see if you run that program. But let's see how the training works. I want to train the card pull for 1,000, let's say for 100 times. And it means that 100 times I will update my Q table. 100 times the rewards will be updated. Yes. So let's start, see what will happen. Sorry. I'm still using the pre-trained model on this. Set this to false. Let's see, look, this is what is happening during the training. Every time it falls down, the environment is reset. See, every time it falls down, the environment is reset. We don't have a visualization for training. This is after, okay. We don't have visualization for training. These are the rewards for testing, actually. So these are the rewards for testing. It means that if I train the network, the Q table, actually, for 100 times, I get such bad results. See, I get such bad results. Do you remember in the previous case, we had a reward up to 500, but now we even don't reach 14. So what does that mean? We will go deeper to this code in a bit, but I just wanted to show you that the number of times you update the Q table is very essential. Is that the number of episodes that you update your Q table is very important. So in this case, 100 times, and then I froze the Q table. I didn't update it anymore. And then I tested it for 10 times for 10 different initial values. And you see how bad it is. Then what I have done is that I have saved my models. I've saved my models after 1,000, after 10,000, and after 100,000 episodes. And now let me upload them. I set this flag to true so that we use the pre-trained model. Set this. Yes.
System learns more when the training episode is.
Yes. Yes. Let's say I'm walking from board to the TV 10 times or 10,000 times. the more I walk, the better I learn. Yes. So I learn in each situation, which action is better to take. And now let's say I go for 1,000 times. So I have saved this. I have saved this. I have saved this, and I run it. See, if 1,000 times is better than 100 times. Yes, was it better?
Same result almost. It didn't reach 40.
Yes. Let's see if it is 10,000, what will happen? It is better. So after 10,000, after actually training is not happening here. What is happening here is just testing. So I've saved these values before. It is a bit better. No,
Yes.
75. Okay, then let's go for 100,000. See how it will be.
It's not the result for one.
No, it doesn't have it. We don't have it, is it? 100, and what did I write here? Is 100. I think somehow I have, this has 5 zeros. That's I think somehow I have overwritten on 100,000. So it doesn't take that much time. Let's run it then for 100,000 times. And it will automatically, it is, yes, let me run it. Then you can see also how the training is happening. So every 100 defaults. So what is happening here? Do you see the rewards here? You see the rewards are getting bigger. The ones which why every 100 episodes, the reward is being reported. So now we have like average of 60, then it's going higher, like average of, we saw 190, we got also already, the reward is getting more than 100. And
200 something.
yeah, we saw 200. And you see how random it is?
But can you change how many times it records the actual? Like you said 100 and then it updates to the table.
No, so by default, I'm using the defaults of the system.
100.
It's 500.
Ah.
So maximum 500, or if the poll falls, it will stop. So
No, I mean the you said after 100 tests it saves and then updates the table.
each 100 tests, it shows us the reward. And yeah, now we have 1,100 tests. And yes, after that's finished, then for 10 times we have test. It means we don't have training. We just use the Q table, but we don't update it.
Okay.
Now we will see how we use the Q table. So we are.
So you mean it doesn't update the Q table based on this test, this training?
Now it is updating. Now it is updating.
Like big and small.
Yeah.
If it's learning from the previous rewards.
Yes, because we are in new conditions. So not every state is visited before. Yes, if a result is if each state is visited many times, if it is visited many times, then it gets better. I mean, in that specific state, you know what is the best action, and you take that action. But not always. I will talk about it. Not always we take the best action. Not always we take the best action. There is another thing that while the training is going on, let me go to somewhere in the code, which is Epsilon. Okay. Look at this part of the code. You see this argmax? This is the formula that you saw on the board. That you have a Q function, which is telling us, so you have a Q function. This gives us a row of that Q function, Q table. So you have a Q table. This gives us a row of that Q table. And this function gives us the index in which, the column in which the value is the highest. So this is giving us the best action, the best reward. Yeah. This is giving us the index of the best reward. And because the index is the column number, that index gives us the action. So we choose action here based on the values which are in the Q table. But you see there is a random story here. Now in a bit I will explain it. We have a little bit left. Then I will show you what that means.
You said 500 is the max for the reward.
500 is the max. You see, we already reached.
Yeah, 500.
We already reached. Sometimes we reach 500. Yeah, sometimes after when approaching 100. Anyway, let this go, and I will now stop sharing and tell you a story about the fact that not always we take the as
Doctor,
action. Yes.
really quick. I noticed in the code there was something called epsilon min, and I just forgot what the min part did. The minimum.
The minimum
Yes. No, I
in the
like.
code, in the code that I showed right now.
Yes, if I'm correct.
Let me go back to the code. Where?
I don't remember exactly when, but like I remember we even saw this in class. It was like a dot min. Go up maybe.
This one? I got it. When you have the when you implement the Epsilon-Greedy, yeah.
Yep. Yeah.
You have the max, not the mean, yeah.
Yeah. Is that where like it sees the max amount of epsilon? Oh, is the epsilon min just the lowest amount it can go to?
This is the minimum, the lowest value of epsilon. Now I will show
Yeah.
you, I will tell you
So
what
it will
epsilon
keep
is.
decaying, sorry, until it gets to epsilon min, right?
Yes, correct.
Okay. Thank you.
Very correct. So let me tell you a story. Let me tell you a story. Imagine that you are new in the city. You are new in the city, and there is no navigator. You have to learn that city, or let's say forest, yourself. And you want to go to work, or you want to go to the university. What would you do? You have a photo of the university, or even the name of the street, but you have nothing else. The city is not that big. What would I do? I would go out, look around the home, and go a little bit farther. I will go left and right, and till I see, let's say, the building of the university. I saw, let's say you want to reach Burj Khalifa. You see the building, and your first guess is that if you go toward it, you can reach it. Not always it's correct. Or you may not see it. Anyway, you have to try many different ways. When you start, when you are new in the city, what would you do? You just explore. You go to every possible way. You don't think that much till you see a sign which could be considered. But even that sign you cannot really trust. You saw Burj Khalifa, but yeah, you should be happy that you know that at least you don't go backward with high probability. But anyway, your hypothesis that the way that you should go to Burj Khalifa may change. So you say that yesterday I came here, I saw the building in front of me, and I thought that if I go directly, I will reach the target, but it didn't work. I tried the wrong way. Actually, I went backward, and then I could reach it. So what does that mean? It means that at the beginning, you just explore. Then you update in each junction, in each exit, you write a value. You update that value. And then listen on the fact that by trying from then on, you could reach the goal, or you couldn't reach the goal. You went so far from Burj Khalifa that you were sure that you will not reach it. You came back. You reduce the number of exploration by time passing. Not at the beginning, but by time passing. It means that one day you come out, you try to reach it, it gets dark, or you get tired, you go back home. Hopefully you find the way back home, but about that we are not talking. The next day, you take the way again and again and again. The more you learn from the city, the less you do crazy decisions. You make crazy decisions. The more you know, the less you explore. If you act based on your knowledge, we say we are exploiting. So we have two different way of choosing actions. You are either exploring or exploiting. Either choosing action, explore, exploit. What is the difference? So explore means let's say random. Exploit means logical. Explore, it means when you go anywhere, it's more likely to happen at the beginning. More at the beginning, or at the beginning This one for at the end. Perhaps the beginning and end are not the best words. After gathering experience. So after you gather experience, you exploit. It means that based on your experience, you take action. But at the beginning, when you don't have experience, what you do is you explore, you take random actions. But anyway, even if you take a taxi driver that knows the city very well, he may not show, even you see sometimes you don't follow the navigator and you find a better way. If you ask locals, they don't follow navigators, right? Because they have had, because to some extent they were using the navigator, but perhaps they got bored or they didn't, they said, perhaps I can find a better way. They took a random action on a junction. They didn't follow the logics. And as a result, they find a better way than the way that navigator would suggest. It means that this exploration should never stop. Should never stop. Because even if you are the best taxi driver of the city, sometimes and on the weekend, perhaps even you are out with your family, say, let's go this way. We know that the building is like 500 meters from us, but let's go this way. Perhaps we will find something that in the future we are just evaluating. You wanted to go there, the goal was there, but I want to take this crazy, non-logical way to the right to just see what happens. This is the exploration. Let's say at the beginning, picture here. Okay, let's say at the beginning, let me use the terminology which is inside the code because our reference is the code. Yeah? I said with the probability of epsilon, the way which is also written in the code, with the probability of epsilon, I will explore. With the probability of epsilon, I will explore. What do you think? This epsilon at the beginning of our learning should be higher or lower at the beginning? So the probability of exploration means crazy actions. When you are new in the city, is that epsilon high or low? It's high. It is high. So at the beginning, it should be higher. Then by time passing, it should be less because you have already learned. Sometimes you do crazy things, but let's say when you are late, you do not explore, you exploit. It means that this epsilon, by time passing, should be less. Yeah? By time passing, it should be less. If you look into the code, there is a parameter epsilon decay. This is the speed of reduction of epsilon. This can be implemented by subtraction or by division, or let's say by multiplication. That will go into the code. Now we will see. So, At the beginning, epsilon is high, and then epsilon is reduced. Let me go again to the code. So I will share the screen so that you can see the code.
Epsilon.
And it shouldn't reach 0. Yes.
You said you should explore like even after you reach.
Yes, very correct, very correct. So let me share the screen. So at the beginning of the code, you have this epsilon.
So we can watch from. Yeah, we can like see from.
So we have epsilon, which is 1. What does that mean? Means that the probability of exploration is 100%. At the beginning, you don't follow any logics because the Q table is empty. Even if it has values, you should not trust them. Yeah, you do not trust the values inside the Q table at the beginning. It means everything is just crazy. I have put 1 million. That's good. I will save it for the future. It's also entertaining to see that. It was a mistake. Anyway, I have the initial epsilon. We say that epsilon should, as you said, the epsilon it should go down, but never to 0. What does this mean? It means 2%. 2%. If 1 is 1%, 100%, 2 is 2%. It means the probability of taking crazy actions forever is never 0. It's, I mean, at one time reaches 2% and it stays at 2%. So it starts from 1% and then it goes down and stays at 2%. You have an epsilon decay. Let's see how this epsilon decay is used. So you have epsilon, which will later be used. You have the epsilon here. In each, this is very, very important. In each, at the end of each episode, not action, at the end of each episode, it means once you try to reach Burj Khalifa, you finished, you were successful or not successful, then you reduce. Not at each step, not at each junction. It means that I don't know the city at all. I'm new, but on each junction or after each step, I'm referring to my memory, the memory that I don't have yet. So don't do that. You go to the end of the episode. You tried everything. You found it, or it's under the sunset. You should go back home. Then in that condition, you update the epsilon. You say, next time, now I have learned something. Next time I can refer to my notes, which are in Q table.
But this when it decays, after it saves the results, and then you said after every 100 test it saves.
No,
And then
after
it decays,
no,
or-
in this case, after 100 steps, after each 100 episode, it shows the reward. Because-
okay.
But after each episode, it is
decay.
it is being saved. I should after in this case after
Then-
each step, after each action, we are updating our Q table. Yes, after each action, we update the Q table after each action,
Yes.
but we reduce the epsilon after each episode. So on each junction, I record going to left, right, or back is better. Or actually I go to one direction and then I record my results on each junction. Yes, but I reduce the epsilon after I'm going back home. Yes, after the episode is finished. So, and what is this max here? It means that you reduce the epsilon. This is the reduction. You see this multiplication to a number less than 1. Epsilon is a number less than 1. And you see it should never be less than minimum. It means that if one day this is less than the minimum, the maximum of them will be the minimum. Yes? So this guarantees that the epsilon will never be less than minimum epsilon. So let's go to choose action. Choose action. Now we should understand this part of the code better. This argmax gives us the best action based on our notes. Yeah, based on our notes, it gives us the where do you write our notes? In Q table. In Q table. The Q table is a two-dimensional table. This will give us a row, and argmax means that the argument which gives us the max, and the argmax gives us the index of the highest reward, which is the best action. So if you look at this Q table, each row, each column is an action. Yes, the index of that column is actually the index of the action. Correct? I will show that in a bit, but it will be more understandable. So this is the so with the probability of epsilon, you generate a random number. With the probability of epsilon, that random number is less than epsilon. With the probability of epsilon, you take a random crazy action. And with the probability of 1 minus that epsilon, you take a logical action. By time passing, this is less and less. So the probability of that randomly generated number is in a range between 0 and epsilon will reduce. Yeah. So by time passing, so this is a random number between 0 and 1. Between 0 and 1. And yeah, between 0 and 1. And by time passing, epsilon gets smaller. So with the lower probability, that randomly generated number is less than this. So if this is 0.02, with a high probability, the number that's being generated with a 98% probability is bigger than 0.02. Now I will show you in the video. I mean, I will act to, and you will see why this is the case. So choosing action. This function chooses an action for us based on epsilon. Why? So this method, because you're going for the maximum, is called greedy. Is a greedy method. Yes. But because I have an epsilon here, we call it Epsilon-Greedy. So this is a terminology. If someone asks you what is Epsilon-Greedy, you say that I take random actions with the probability of epsilon, and with the probability of 1 minus epsilon, I take logical actions. The logical actions which are greedy. I want to have the highest reward. Then let me go and show you why this part of the code that works actually. Let me write down the code. It is pseudocode. You have a random number which comes from the random function, and you say if this random number is smaller than epsilon, you explore. It means that you take, let's say, explore, and you exploit. So what does that mean? Let's say I have let's say this is all, so yeah, let me, now I think it's too close. Sorry. So I wrote the code here. You have a random number, you save it in a variable rand, and then you say if rand is smaller than epsilon, you explore, else you explode. I want to understand how this random number can help us with this. This is just a technique. It's not limited to reinforcement learning, but there may be another way to implement it. Just as I want to see how this is happening. So let's imagine that I have this is a wall in front of me, the one big one in front of me, and these are columns by color. If I throw this with a probability of 100%, it will hit the wall. So with the probability of 100%, it will hit one of them. So let's say they have index 1 to index 100. With the probability of 100%, this will hit one of them. Which means that, let's say if my epsilon is 100, epsilon is 100, and if I throw this to my wall, with the probability of epsilon, which is 100, this will reach the wall. Yes. What if I reduce the epsilon to 50? To 50, it means that I consider just up to the index 15. I consider just to the index 15. And if I throw this with the probability of 50%, it will reach the part of the one that I want. Yes, this is the way this is working. So you generate a number. You generate a number. Generating that number randomly is equivalent to throwing this. Where will it land? Generate that number randomly. Then you see if that number is less than epsilon, you act in a way. If it is bigger than epsilon, you act another way. The epsilon first was 100%, and getting reduced, it goes less and less. By time passing, probability of this landing to the part of the wall that I want, it means less than epsilon, is less and less. One time it will reach 2%. This is how Epsilon-Greedy is working. This is how Epsilon-Greedy is working. Then I think I am speaking for almost 2 hours non-stop. Let's have a break for me. Then let's say in 10 minutes, let's be back. Yes, can you hear me? Anyone?
Yes, doctor, we can hear you.
Okay, thank you. So let's look into an animation. There was an animation. This is the updated one. So some of the students asked me about the states and actions and when do we update, when do we move, and so on. So students are coming back. So now I'm showing how states and actions and rewards work in in an example. So let's say this primitive person is going to go home. So the goal is reaching home. This is a family. This is a family of let's say reinforcement learning problems that the reward will be given just at the end. The reward will be given just at the end. Can you hear me properly? The students who are online, can you hear me very well?
Yeah, we can hear you.
Thank you. So the reward will be given just at the end of the episode. Someone asked me, what is an episode? An episode is one time when this guy comes out of home, either gets killed by an animal or gets lost, or it gets dark and goes back home. Let's say he cannot take more than 20 steps or 10 steps. Each step is like say 1 hour, and then he should go back. When he goes back, we say an episode was finished. And the best case is that at the end of the episode, it reaches the goal. So an episode, so this is not an episode. An episode is when you see it is here, or the person is at the goal or has gone back. So what does this guy do? It looks, explores. It's looking to, let's agree, when he's half on a wall, he's reading. So he expects something being written there, and perhaps it's written that way is good or bad. So at the beginning, actually nothing is written. So anyway, he reads. Then next time he takes an action. Did you see what he did? He is still here. He reads the wall. He reads with the wall. So this guy wants to go from here to here. What does he do? On each wall, it's written either going this direction or this direction is good or bad. Is good or bad. He reads on the wall. So he's still here, but he's reading. So I showed reading by putting half of the body here. He reads, nothing is written, nothing is written. He takes an action. He goes to the right. He goes to the right. Then he looks, he reads, nothing is written, nothing is written. It goes to the right. He doesn't read, he just takes an action. This was the crazy action, exploration. He took an action without reading. It was exploration, yes? Then he saw it's bad. It went back, he went back. Then, and he wrote on the wall, let's say, he was here, it was bad, wrote on the wall that, hey, here is bad. Then he was here, he read, but anyway, he took an action back. So he's exploring, not always based on what is written on the wall, but he reads, he's sometimes acting logical, sometimes acting crazy. Crazy means exploring. So he comes here, reads, nothing is written, and then takes an action. These are just random. Yeah? Takes an action. It was bad, writes that this spot, but it was bad. Comes here, it was bad, writes. Goes here, nothing has happened there. Then he comes here, goes here, nothing. Comes here, it was bad. So and so on. Yeah. So he is just recording that it was bad. Nothing has been good. He reached home. Yes. He records just at the end. It's the first time he's getting a reward. This is one family of artificial reinforcement learning problems. Just at the end of an episode, you can get a reward, but the reward will be back propagated. So he moves again. So he look, he came to this state, and in this state, he saw that, hey, it is bad. Then he marked the state as bad. Then he goes, so each time he reaches home, So the value of this state goes higher, yeah, it goes higher. And at the end, he has such indicators that, let's say, if you are here, here it's not evaluated yet, for example. Here it doesn't matter if you go to right or left, but if you are here, it's better to go here. These are just, I have put them randomly. There is no logic here. Nothing is calculated. I made this animation myself. It is just an example to show you that the reward is back propagated from the end state to the beginning. Yes. And so now what we talked up to now was Q learning. Yeah, it was Q learning. Then there's another way of learning. It is called SARSA, state action reward state action, SARSA. So SARSA, state action reward state action. It has a difference with Q learning. Now I will tell you what the difference is. Imagine such a, yes,
State action, no.
state action
Yes.
reward
Yeah.
state
State.
action. Yes. So imagine such a situation, you're in such a situation, then he's asking himself based on the records that he has put on the, based on the marks that he has put on these walls. And yeah, he wants to make this decision. Going right is going, how good is to go to the right? How good it is to go to the right? Because he should know how good it is to go to the right, bottom, left, or back. He should know to then to take action. So how good it is to go to the right? It's a question. So you see that there is a way. There is a way here. So if he just looks to the right and he's aware of the future, he knows that from here on, there is a way. So if you go here, there is no way to reach the goal. But from here, there is a way to reach the goal. So there is a way to go to the right. So is it then a good action to go to the right just because there is a way to go to the right?
If now it's equal for him, you go right or bottom.
No, we are just talking about the right. Now we want to evaluate going to the right is good or bad. Yeah. So if after going to the right, he goes to bottom, it's good.
Yes.
Yes. So if you know that this is a logical person that acts based on the documents, then going to the right is good. Yes. This is Q learning. So if you think like this, if you trust the agent, actually not to trust. If in the evaluation you suppose that he will take the best action, then it's Q learning. But it can be that he goes there and he does something crazy, but you just don't care. I say, in the future, there is a good, I mean, in the next state, after the next state, there is a reward which comes from one of the actions. The reward is high, I go to the right because I trust, I mean, when I'm evaluating, I know that I may go somewhere else, but in evaluation, I consider just the maximum. Yeah, I consider just the maximum. This is Q learning, but you know that there is always a probability of doing something crazy. If you are honest to yourself, if you are honest to yourself, you know what you will do in the future. So you are a little bad child. You know that you should not, I don't know, eat cube sugar when your parents are not at home. But you know that when they leave, you will do this. Yes. So you will consider this as evaluation of the currency. Your parents are going out. If the parents trust you, it is a Q learning. If they are realistic, they know that with which probability you are going to eat that sweet, and they consider for evaluation. in fact in the future you may not take the best action, and then they honestly ask you, honestly tell us what you are going to do. If you are going to do a bad thing, they consider that bad thing for evaluating the current state. If they are honest, I mean, if you consider the future reward not the best future reward, not the best action, but the action that really will happen, then you say this is SARSA. SARSA, based on the policy. Policy is the character of the agent. Based on the character of the agent, predicts what is going to be done by the agent, and then it updates the Q. So look, you have a Q value here. You have a Q value here. The Q value is being updated. It means something is being added to it. A portion of something is going to be added to it. What was that something? Was the difference between immediate reward and the recorded reward plus the discounted future reward. The story of greediness is here. If someone always, I mean, the one who's evaluating, always consider the maximum future reward, then it is Q learning. We say off policy. Off policy. Policy means the character of the agent. Off policy, it means I don't care about who you are. You're a bad child or a good child. I always consider the best thing that you would do, and then I evaluate the current state. So here, when I want to write the reward of future, I see what is the maximum reward from the next state on. This is the maximum reward from the next state on here. This is Q learning. This is what we have learned up to now. But there is another method which we said this is SARSA. Look, we don't have that maximum in anywhere here. The maximum is removed. We just give the Q value. We just give the Q value. And the action comes from a policy. It is from the character of the agent. And this actually can be sometimes random. Sometimes can be say that with the probability, the state will take the agent will take the best action. So this has here we can have different stories. Yeah, here we can have different stories. But if it comes, if it is realistic, then it is SARSA. So we didn't. So this is the Q learning. It has a max. SARSA doesn't have that. So this is the difference. Everything is the same. This R could be written small. I just wrote it big so that it's more visible. Everything is the same. The only difference is that we don't have the max in SARSA. So this is best future reward. This is the actual in SARSA. We have actual future reward. Okay. This is we may have time to go through this. Actually, I'm teaching you upside down. In order to come to SARSA and Q learning, one should first know Bellman equation, and before that, one should know Markov decision model and Markov reward model. But now we have an applied course, and yeah, I'm teaching you from back to beginning. So what is I'll tell you shortly. This will, in the midterm, we will not have this. It's just from where, if you look at lectures and go to the literature, you will see that this Q learning comes from Bellman optimality equation. Optimality because in that equation also we have the optimal reward or maximum reward. I don't go deep to this. we have the probability of taking the next, being in the next state, the probability. What is the most probable or least probable state after taking the action of A in the state, in the current state? To this, we will go later. Just I want your eyes to get used to this. So, yeah. So for now, I will stop. So what for the exam, for the midterm, we will from this presentation we will have up
Doctor,
to here. So yes,
just really quick. You said the only difference between key learning and SARSA was the max, yeah?
yes.
Now, I just forgot what exactly does the max do? Like, does it just take the best what do you call it? Optimal reward in this situation?
Yes, look. Here he wants to go to the right, and he wants to consider of the also the how good and bad that state is. From that state on, the situation is, yeah, from that state on. So this is the you take action A, then you go to, so you're in state S. You take action A, you go to the state S prime. Yes, you go to the state S prime, and then from that you take action A prime, the action A prime, and that then you go to here, or you go to here. Let's say the action A prime is coming to this direction.
Yep.
And it will give you a different reward than if you would go to this direction.
Yep. Because I remember you said key learning always assumes that the next step will be the best step, right?
The best step in the next state.
Yeah, in the next state.
Yes.
So, what's it called? Like, would it really be assuming if it knows that the reward, for example, to taking right would be better than the reward for going down?
What would be considered?
Like, does it actually assume whether or not
No, he doesn't assume. It's written in the Q table. He goes, reads in the Q table and sees that. So in order to see if taking this action to the right, how much reward we have, you look into the Q table. And from here also, you look into the Q table and you look down how much reward you would take if you go to this direction.
Yep.
Yeah, it's both all information about rewards come from Q table. No matter how far you go.
So in that sense, what well, why would I use SARSA instead?
Very good question. It can be, so first of all, it can be that your agent by nature has a random behavior. Yes, you have an agent, a car or something, but it's more probable, to use, more popular to use this method under the condition that the word itself is not predictable. It means that yesterday going here was good, today is not good. So you consider it probabilistic. So statistically, it is good to go to this direction, but it can be that going to this direction is better. So that's why we first look and then we decide. So the reward is an interaction between the agent and the environment. The statistical behavior of the agent and the environment itself that will bring the different rewards to you. How that is trustable. If you trust it strongly, go for Q table. That you know that this is very probable. So for Q learning, very probable that your agent will go to a direction that brings the highest reward. But if you know that because of the specification of the region, or I mean the environment or the agent, you cannot expect that in the next state, your agent will or can take an action which brings the highest reward. You would better first study and then first see where the agent will really go.
Okay, I did not understand that last step.
Pardon me?
That last part, I did not understand it.
So let's have a simplified like that the child which is at home. If you know that anyway, because of the age of the child, you cannot expect that he will do the best thing. You first predict based on the fact that he has eaten chocolate or not, has slept well or not, predict what he will do, and then you evaluate the situation. You don't say that I know that he is a good boy and will not do this and that, and I evaluate. So if I let him to the room number 3, then room number 3 is good if he doesn't jump out of the window. But there is a probability that he will actually jump out of the window. That is a problem.
I see.
Yes, my computer is
So
dying.
is that why SARSA would sometimes be better than Q-learning?
Yes, in unstable. Yes,
Yeah, because
sometimes
certain actions may lead to worse outcomes, even though they seem like the best actions at times.
Again, please.
So like Q-learning would be sometimes like SARSA is better because even though that may seem like the best action, it could lead to a worse result. Is that what you were trying to?
No. It can be that we will not take the best action.
Mm.
We will not take the best action. If the probability,
wouldn't it be seen as the best action due to the reward that's given out?
Yes. So it means that although it is documented where the best action is, that means where the best reward comes, or under which action we get the best reward. Although we know that, but we may be that we are not going to follow that. It means that the nature of the agent is, let's say, stochastic. It's not predictable. The character or the policy is like that, or the environment is changing. Yeah.
So basically, like the environment might have changed. So what was the best reward back in the day is no longer. It may no longer be the best reward today.
You can say it like that. It means that the agent is going to take the best reward, but the best reward is the best action. But actually, the best action may be not already the best action, or you can be that say that the agent may by character may not take the best action. So I'm more realistic. So in unstable situations, let's say we say unstable environments, SARSA may be better.
I see.
Yes.
Okay, thank you.
And then let me. The other presentation here. I had this also, the maze, the code of the maze also shared. If you remember, I will stop this, uses the Q learning on this. If you remember, we had this maze, the code is shared. This agent wants to move from the beginning to this goal, wants to reach the goal. If it goes to a wall, it gets a negative reward. We call it also punishment. And the negative or positive reward is also propagated through the through the gamma, or let's say not through the gamma, through the future rewards. I mean, the portion of it which is actually the strength of gamma is considered for evaluation of it. So you are in this step, and you want to move to the other step. You have not reached the goal, but because of the future rewards that you have, your current state gets updated. And just, you see, just if you reach the goal, you get a positive reward. So here, either the rewards do not change, or either they do not change, or they got less, they get less. And you see, this reward is increasing, and as a result, you see this reward also is being higher and higher. Yeah, each time this ball can reach the end. I have shared this code for SARSA and Q-learning. I will stop it, and I will show you pictures after 10 episodes. You see how it looks like. After 10 episodes, here is closer to yellow. So yellow is higher, red is something in between. So let's see, this positive reward is being back propagated. After 100 steps, here's already yellow. And here is orange. And the positive reward has already reached the initial state. So it is being back propagated. But in cardpool, you didn't have a goal. In each step, you could, or you actually do update the Q value. Let's go to exploration and exploit. This is the last topic for today. That this exploration and exploitation can be packed together. So we had this SARSA and Q-learning. SARSA and Q-learning, the difference was that in SARSA, you consider the actual future rewards. In Q-learning, you consider the maximum future reward to update the current reward or recorded reward. So this is recorded reward. This is immediate reward. And this is the future reward. On the board, I have written this here and this here to show that we are talking about difference. So review, these are Q table. You have different states. Let's say we were in the base, we were in the cell number 1. Let's call it, we can also state number 1. These are our states. We have 4 different actions, right, left, up, down, and each of them has a reward. Each of them has a reward. And this was the way that we chose these actions. If you wanted to act crazy, it means exploration. Exploration was done with the probability of 1 minus the epsilon. That means if the epsilon is 1, with the probability of 0, we exploit. It means with the probability of 0, we follow the logics. If the epsilon is 0, which means probability of 100%, we follow the logics. And we say it's advised not to put epsilon to 0, so to always be able to explore. So if we are here using exploitation, then what do? We look into the Q table and we take the highest reward. We see which action has caused this highest reward, and that action is chosen. So for example, here we have under cell 1, which is state 1, under state 1, if we take all actions, the one which gives the biggest reward, which comes out of these cells, is 0.8. If you put this A under it, which is called argmax, it means the argument which made this max, then this action is down. You see, this is a state. Under this action, we took the highest reward. So max gives us the highest reward. Argmax gives us the action which has caused the highest reward. And in cell 2, the highest reward is 0.7, and the action which has caused that is the action right. So this is when we are doing exploitation. We are following the logics. What is logics? Logics is what is written in Q table, what is recorded. It's like that we are reading books and then we are acting in our life. So how can you understand this? One can show this like in this diagram. So you actually are iterating, you are searching. You are first here and then you go here, here, here to see which of them is the biggest. So first you look under your first action number 1, what is the reward? You suppose that this is the highest reward, then you go to the next, you look to the next action. If you go left, the reward will be 0.5. Then you go up. You look actually what will happen if you go up. You are reading, you are not acting. And then you look what would happen if you go down. So the reward is 8. This is the maximum reward, the best action which comes out of argmax. Argmax is the action which gives us the best reward. So the best action is down. So we talked about exploitation. Exploitation means following the recorded, documented actions and rewards. But I showed you this code. You remember that we have exploration and exploitation. By exploitation, we were using the Q table. We are using the argmax, which gives us the best action. But and yeah, that I'm repeating it. About this, we jump over this. But we know that not always we take the best action. Not always we go to the documentation, to the Q table to see which action has the best reward. In the Q table, we have the rewards actually. We don't always do that. With the probability of epsilon, we may take a random reward. The probability of epsilon, we will take a random action. A random action. So here we had 2 conditions. We had a, let's say, coin. We had to flip it to see where we will land, here or land here. But we can also combine these two together, and write such a formula. It's called softmax. This is a specific version of softmax with a tau in denominator of this exponential function. What does this do? So we have rewards which come out of our states and action. We take one action. Say how probable is to. So you want to choose an action. Say how probable is to take that action. How probable is that that action is good, or how probable is that I will take that action? So how probable it is? I will write this E powered by the reward that you get out of that action divided by the tau. I will say what that tau is. And then in the denominator, you have the sum of all rewards of all actions that you could take that in that specific state. So in each state, you can say, you can take, for example, 10 different actions, 10 different actions, and 10 different actions bring 10 different rewards. You write all of them here, and the reward that you're focused, I mean, the action that you are focusing on would bring you right here, and this will give you the probability of taking that action. So this is called softmax. The tau is actually making the formula interesting. Tau is the temperature. The higher the temperature is, it's like you see it also in large language models like GPT and other similar methods. Models, that the higher the temperature, the more random the model behaves. You reduce the temperature, the model behaves less random. So how does this work? If tau is big or if tau is small. If tau is small, what will happen? Let's say tau is 0. Temperature is 0. What would happen? And if the tau is 1, what will happen? So if the tau is 1, if the tau is 1, then the probability of taking each action, I mean, the probability of taking all actions will be the same. It means they have the same probability of being chosen. And if the tau is small, the probability of being chosen is a function of the Q value itself. So how does this work? You put them in this formula, and you increase the temperature. If you increase the temperature, the probability of these actions becomes similar. The probability of these actions becomes similar. It means that it doesn't care which of them is higher. It takes one of them.
Doctor,
But yes.
I'm sorry. I went for a second. I came back. What's the functionality of tau?
Okay, tau is the temperature. The higher the tau is, the more random, it means out of logic, the model behaves. Yes. So if the tau is big, you see the probability of all these actions. So you had action 1, action 2, action 3. And if you are in a state, in this one of these states, is just an example. The action A would bring 5 rewards to you. The action 2 will bring 2, and action 3 will bring 0.5 rewards. So it means that naturally this should have a higher probability to be chosen, because has a higher reward. But if you put them in this formula, that means you sum all of them here and put just one of them on the top. If the temperature is high, if the temperature is, let's say, approaches infinity, then if the temperature approaches infinity, this will approach 0. I think I mean, a bit earlier I said 0 and 1. No, the temperature, if the temperature goes to infinity, this will approach 0, and then this will approach 1, and then this will be just the count. So it means for each, so if you have 3 actions under the condition that the tau is infinity, the probability of each of them will be 33%. It means 1 divided by 3. So if tau goes high, all actions, if tau approaches infinity, all actions will have the same probability to be chosen. But if the tau is less, if the tau is less, then if the tau is less, then the one which has the highest probability by nature will have a higher probability to be chosen. Look,
So, doctor,
uh,
in a sense, the higher the tau, the more likely it will explore.
yes.
So, what's the difference
Very,
between this and Epsilon-Greedy?
yes, very good. So when you were not here, we said that we had this Epsilon-Greedy. We had the Epsilon-Greedy, which had the condition. So you have a random number, and that you, based on that random number, you decide to explore or exploit. But if you put them together, if you combine them together and you come to, you use, we call it soft max.
Yep.
If instead of argmax, you use soft max, this is soft max, then you don't need that condition. You just set the temperature. You just set the temperature. The temperature tells how random the behavior of the agent is. If the temperature is higher, the behavior of the agent is more random. If the temperature is lower, if it is colder, the agent is more logical. So by this, you regulate how random is the agent going to behave. This is equivalent to this. So in your codes, in one of the labs, you have turned Epsilon-Greedy to softmax. Yes. So in that lab, you could simply remove the epsilon, because if you use the softmax, epsilon is not used at all. You either use Epsilon-Greedy and you use this, or you use this one and you don't need the epsilon. So this is, these are two, and I mean, they are almost the same thing. Almost the same thing, but with this you can regulate. Here you have more freedom. Here is more restricted. You have also a random variable, but here you can even learn the tau itself.
I see. Now, doctor,
Yes.
it's all just represented in softmax, right? I don't need to do like I don't need to do it the same way we do epsilon, because epsilon, like, it's almost like we write a formula to do it with epsilon underscore min and then comma and then, like, the decay part.
Yeah,
So
naturally.
here we can just do softmax and it works exactly like you explained.
Yeah, here instead of decreasing the epsilon, you decrease the temperature. At the beginning, you have a high temperature. The agent is acting crazy. It's just exploring. Then you reduce the temperature. We say the person has a cool head. It will follow the logics. So at the beginning, high temperature, then the tau goes down. You will have less and less tau. Then that will cause more logical behavior.
And does it matter whether I use softmax or epsilon? Like, or do they or does it just not matter?
In simple problems, no. But if you want to dynamically, you can learn the tau itself. If you want to have more freedom, if the problem is more complex, then softmax may help. And softmax is just an example of softmax. Softmax usually doesn't have this temperature. In reinforcement learning, we have this temperature, but softmax in classification also we use it. In the other class when I was teaching the Bayesian classifier, I also there mentioned softmax. I mean later I will also go to that. And no, so here, yes. Then, so in this diagram you see that the probability of taking a logical action under zero temperature is higher. This is the best one. So this is PA, which has the highest reward. And if you increase the temperature, then the probabilities approach. So just in the temperature 5, they are very close to each other. So if you want to show that on a diagram, here you don't go for the maximum. you talk about the probability. So it means that here it is highly probable that I will take. So here if you remember when I was showing this diagram, I'm pointing to exploitation. Yes, I'm pointing to exploitation. So this diagram is for exploitation when we talk about Epsilon-Greedy, but this diagram, in this diagram, we don't have exploitation, exploration. We have the probability of exploration, exploitation. They are not separate from each other. They are connected with each other. Yes, that was it. So from in the midterm, we will not have deep Q learning. So we will not have the neural network that I was teaching the last in the last session. This what I taught today is actually, I don't know, 4 lectures, 3-4 lectures together. This will is common in applied AI and AI courses, but there are two topics that which are different in applied AI and AI, which I will tell you separately in each class next week. And many students had asked, so what should we learn for the exam? I would start with the code. So for example, one important aspect that today I say, when you are decreasing the epsilon, if you use Epsilon-Greedy, you decrease it after each episode, not after each step. And you should know why. So in the code, you can see it, and you should be. So did you see how I was telling stories? Understand it as stories. You tell each other about this topic, sit and analyze the code. So actually the amount of things that you should learn is not that big, but you should understand them deeply. The code is the reference. So you understand, if you understand the code, then the code and the presentations are actually following each other. But in the presentation, you cannot see the sequence and what is done when. I would go to the code and then use presentation as the reference to understand the code if necessary. And the questions which are asked in the labs, those are very important questions, and the programs that you have written yourself. So I would say the focus will be on the labs and the codes. And the
Doctor,
presentation,
which labs specifically?
all of them.
All of them?
Except the last one. So all of the labs are actually just either Q learning or SARSA, but actually you are just repeating the same thing. In one lab, you have analyzed the code that I have written. In the other lab, you have written a code based on the code that I have given to you. And if you pay attention in the lab instructions, there are questions. So you pay attention to those questions, but it's not limited to those. I mean, the nature of questions will be like the questions that you see in the labs, the nature of questions that you explain. And then after you are done with the labs, you may also go to the presentations. And actually, in the presentations, what could be of importance are just 2 mathematical formula, which you do not see them in the codes. That's it. So these 2, and I will not ask you any question that needs memorization. You do not need to memorize them. Actually, it's just 2 stories. I will give them to you, but you should understand them. And I may give you a code to analyze, but I will not ask you to write a code. So it's just about
So we will not be writing code. We just need to understand the code.
Yes.
Okay.
No question about writing the code. Writing the code will come in lab final.
Oh, okay.
Yes. Yeah, we are done. If you have questions, you can write me emails, and also we will see each other in few days.
Doctor, really quick for the project.
Yes.
Now we had 2 lab assignments, right?
No. These are you have just one lab assignment. The two.
No, sorry. Assignment part A and assignment part B in the labs, right?
So the lab has 3 parts.
Yeah.
Tabular Q learning, tabular SARSA, and deep Q learning. Yeah.
Mhm.
You don't have deep SARSA. Because of some reasons, we have deep Q learning, but not deep SARSA. You can theoretically, but no one does this. But so these things, so 2 of them you have already learned and done.
Yeah. The only thing that's left is the deep Q learning, right?
Yes.
So we need to apply that and then answer the questions, and that's basically it done, right?
Yes.
Okay then.
But there is something, please keep your communications with GPT clean and beautiful. These are, yeah, for yourself and also for, also this is really also a practice for your lab final exam. Just keep them, and when you upload the lab reports, upload your communications with GPT to, the prompt.
Thank you, doctor.
Welcome.
Doctor, if this session is recorded, can you just upload it on Moodle?
It is recorded, so you don't have access to that. Just I have access. Yes.
Yes.
So I will upload it somewhere and give you the link.
Okay. Thank you, doctor.
You are welcome, and yes, and thanks for the many students who are sitting here. And then see you in the class. Do you have questions?
Oh, thank you, doctor.
Welcome. Then see you in the class.
Thank you, Professor.
Welcome.